Hello everyone, welcome to this lecture number 4 on electrodynamics and electromagnetic waves. We have had about 3 lectures, so this is just a continuation of what we've had, mainly still concentrating on the Maxwell's equations. So this is the presentation outline for this lecture. We shall mainly look at the coordinate systems and how these coordinates are important in Maxwell's equations. So first we will look at Cartesian Cartesian coordinates, which we are familiar with. Then we look at other coordinates, that is the cylindrical and spherical. You are also familiar with them, although not so much, because Cartesian is more common compared to these other two. And then finally, we'll pick some questions to see how these coordinates, the cylindrical and spherical, can be applied in Maxwell's equations, and how different these equations are from the normal Cartesian equations. So first, like we've said, that other than the Cartesian coordinates, we have other coordinate systems which can be used in calculations involving Maxwell's equations or any other form of calculations that require some coordinate systems. Remember, these coordinate systems, they basically depend on the reference axis that you're dealing with. Sometimes you can be having an angle that is varying and a side not varying, so you might find at some point you might need different coordinate systems apart from just the Cartesian coordinate. So basically the Cartesian coordinate system uses the variables x, y, and z, and then it is closely linked to what we call the polar coordinates, that is r and theta. So you can convert actually between Cartesian and polar. Yeah, polar is very close to Cartesian. Now, then we have the cylindrical coordinate system, which uses the 3 variables, that is the r, that is the position vector r. Then we have the angle phi, right? The angle phi, you can look at the figures there, and then the coordinate z. The spherical coordinate system uses 3 coordinates, that is the r, theta, and phi. So the Cartesian coordinate, like we've said, uses x, y, and z. So in an electric or magnetic field, the components are labeled like Ex, that is the x component of the electric field. You have Ey, that is the y component of the electric field, and Ez, that is the z component of the electric field. Similarly, for magnetic field, you have component x, which is Bx, component in the y direction, that is By, and component in the z direction, that is Bz. And then don't forget that these axes have what we call the unit vectors. So I denotes the unit vector in the x, j denotes the unit vector in the y direction, and k denotes the unit vector in the z direction. So in terms of the conversion between polar and Cartesian, you can basically have two-dimensional axis, that is x and y, and you have an angle theta that is varying from the positive x-axis moving counterclockwise. So then if a point is in that 2D space, it can be specified using the coordinates x and y, that is the Cartesian, or r and theta. R is basically the amplitude, or it can be E naught or B naught, depending on what is the amplitude. So the conversion between Cartesian and polar is, for example, you can see here, the x component of electric field is just E naught times the cosine of theta. You can derive it here from the figure. Similarly, the y component is E naught times theta, and the same applies to the magnetic fields, where you have the x component Bx and you have the y component By. The magnitude R, or E naught, in this case is simply obtained using the the Pythagoras theorem, which is E naught is equals to Ex squared plus Ey squared. So that is the Cartesian coordinate. Now, again, in the Cartesian coordinate system, we have this mathematical operator, which is referred to as the del operator, denoted by the symbol nabla. So in Cartesian coordinate system, the del operator has three parts, that is the three terms, the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And of course, it contains the unit vectors I, j, k. So using this mathematical operator, we can obtain three equations, that is the divergence equation, right, the curl equation, and the Laplacian. These three terms are actually, you should be familiar with these three terms by now. So divergence basically means you're getting the dot product of a vector. The dot product of a vector obtained using the del operator. So the divergence for an electric field is, as you can see there, the partial derivative of x acting on the x component, the partial derivative of y acting on the y component, and the partial derivative of z acting on the z component of the electric field. Now, the curl simply means the cross product of the del operator and a vector. So when you perform the curl operation, you will normally draw a determinant matrix where you have the I, j, k as the unit vectors. Then you have the center called a row, which contains now the components of the vector. That is the x component, the y component, and the z component. And then in the third row, you have now, the second row, you have the components of the del operator. And then in the third column, third row, you have the components of the vector. So then you simply perform the determinant process the normal way, and this is what you obtain, the equation that you can see there. This equation, you don't need to cram it in your head, provided you know how to operate a cross product, then that should not be something to worry you so much. Then we have an equation called the Laplacian equation. The Laplacian is simply the second derivative of del acting on a vector. So the vector is differentiated two times. Okay, it's a second derivative of the vector component. Remember, these are partial derivatives. So when you have three variables, you consider other variables as constant, but you only differentiate an expression with that particular variable that you're dealing with. So then let's look at now the cylindrical coordinates, because this is a bit not very common. So the cylindrical coordinates is defined by three coordinates. That is the r, the angle phi, and the coordinate z. For example, in an electric field can have three components, that is ER, okay? You can relate it with the EX for the Cartesian coordinate. Then you have E phi, which corresponds to the EY for the Cartesian, and then you have EZ. The other thing you need to note here is that the unit vectors, now they are not I, J, K. Now we have the unit vector R, the unit vector phi, and the unit vector Z. So you have a coordinate system that has three axes for R, phi, and Z. So this coordinate system, this new coordinate system, can also be linked with the Cartesian coordinates. According to the transformation expressions, you can see here that x is basically equal to r cosine of phi, y is equal to r sine of phi, and z in the Cartesian equals to z in the cylindrical coordinate system. That's why you simply have z is equals to z. So let's proceed. The unit vectors r, phi, and z form a right-handed orthogonal triad. Z is the same as in the Cartesian coordinate system. So the gradient operator in cylindrical coordinate system is not the same as the gradient operator for the Cartesian coordinate system. This one is slightly unique. You can see the unit vector r has a coefficient which is partial derivative with respect to r. The unit vector phi has a coefficient 1 over r multiplied by partial derivative with respect to theta. And finally, the unit vector z has simply coefficient the partial derivative with respect to z. So you see, we are not using I, J, K, and again, it is not just a matter of just saying partial derivative of r, partial derivative of theta, partial derivative of z. We have, like in the center term, we have 1 over r multiplied by the partial derivative with respect to theta. So that is the gradient operator or the del operator. So the divergence of in cylindrical coordinate system is also not the same as the divergence in a Cartesian coordinate system. If you look at the term, the first term for the divergence, you have a coefficient which is 1 over r being multiplied by the partial derivative with respect to r, and it acts on the component r times the vector in the vector of that component. The term in the center has a coefficient 1 over r simply multiplied by the partial derivative with respect to the phi, but on acting on the component, the phi component. Let me call them phi component, the r component, and the z component. So you need to really take note of these coefficients. Like for example, this 1 over r, and then you have r, er. The center is only acting on the phi component, and the last one is acting on z component. The curl, you simply need to derive this using the determinant matrix, like I explained. If you use the determinant matrix, you should be able to get equation number 9 clearly. You have to remember that how you arrange elements in a determinant matrix will determine whether your answer will be correct or not. So you have to be really careful with this determinant, how you obtain the determinant of a matrix in a 3 by 3 matrix. And of course, finally, the Laplacian is, as you can see there, you have the coefficients 1 over r, then you have 1 over r squared for the second term, and then the third term is basically, it doesn't have a coefficient, but the coefficient is 1. So what I'm trying to say for the cylindrical coordinate system is that you really need to take it correctly the way it is. If you miss a single coefficient, then your final answer will definitely not be correct. So let's move to the spherical coordinate system. In a spherical coordinate system now, we do not have the z, but instead we have the r, we have theta, and we have phi. Okay, so if you have a vector like E, it has components ER, E theta, and E phi. Again, you can transform from spherical to Cartesian coordinate system using these three expressions down here. And these expressions, by the way, if you are wondering how they come about, just look at the figure here and try to derive them yourself. Okay, that will also boost your understanding of this subject. When you try something by yourself and you get the answer that is provided in the textbook, then you get some confidence going forward. Yeah. So spherical coordinate system, the gradient operator is, as you can see there, it is not directly the same as the others. It has an introduction of some sine theta, so you really need to take care of that and be careful. The divergence, the same. There are coefficients. You can see the coefficients has a reciprocal of sine, and the other first one has a reciprocal of r squared. So you take note of that. Then you have the curl, which, like I've already told you, that curl, you really don't need to worry, because if you know how to do a determinant matrix, then curl definitely applies the determinant matrix method to obtain what you can see there. So these are expressions that you do not need to cram. But if you know how to derive, then you are good enough, because it means even in an exam, you can be able to derive it and then use it. Now, these are the questions. The first one is determine whether the vector field B below represents magnetic field, which is B is equal to 1 over R vector in the direction of R, RZ in the direction of phi, cos phi in the direction of Z. So by inspection, you realize that the vector field B is in what coordinates? It is in cylindrical coordinate system, because you have R, you have Z, and you have phi. This tells you that this is in cylindrical coordinate system. So the solution looks like this. Any vector field that represent a magnetic flux density must satisfy the Gauss law. And the Gauss law is the divergence of B equals 0. Remember this one we discussed, and say this one simply means the magnetic monopoles do not exist. So in cylindrical coordinate system, the divergence of a vector is, as you can see there in equation number 17. So all we need to do here is to identify the components BR, B phi, and BZ. Those ones can easily be picked from the B vector provided in the question, where BR is basically 1 over R, B phi, the coefficient here is RZ, and BZ is the coefficient there is cosine of phi. So in this equation number 17, what we shall do is to substitute the values here for BR, B phi, and BZ. Okay. Once that is done, we will differentiate as per equation number 17. And if the result comes to 0, okay, that means if equation number 16 is obeyed, or it is true, then we shall make a conclusion and say that the vector field B, the vector here, B given, represents a magnetic flux density. So it is as simple as such. So let's proceed and see. So we substitute those components. As you can see, this one is BR, it has been substituted. This one was B5, it has been substituted. And this one was BZ, it has been substituted. So after substituting, then you carry out differentiation. For example, the first term means you differentiate with respect to R. The middle term, you differentiate with respect to phi. And the final term is to differentiate with respect to Z. So interestingly, you see that when you do a partial derivative of a function, you basically concentrate on that particular variable. Okay. So for example, in the first term, our concern is variable R. And if you do the differentiation here, your answer comes to 0. Because what is in the bracket here, R and R will cancel out. So you remain with a differentiation of 1. If you differentiate a number or a constant, what you get is a 0. The middle term, we are told to differentiate with respect to phi. But the term we are differentiating does not have phi. So it is equivalent to differentiating a constant, and that gives you 0. Similarly, the third term, that we do not have z, and so we are differentiating a constant, and that gives you 0. So then the final answer is the divergence of B is equal to 0. So that means our equation number 16 has been proved to be true. Then we can make we make a conclusion and say the vector field B does satisfy the Gauss law and may therefore represent a magnetic field. So I hope now you see partly how you apply the cylindrical coordinates in a Maxwell's equation. In question 2, we are told if the vector field E, given as you can see, represents a static electric field, determine the charge density associated with this field in free space. All right, so the solution looks like this. First, we are told to calculate the charge density. We have 4 Maxwell's equations. There is only one equation that has the charge density, and that is the divergence of electric field intensity, E. So the divergence of a vector is given by equation number 19. Specifically, the divergence of an electric field E is, you can see that, which now will have the component of E will be ER, component will be ER, E theta, and E phi. So we extract these components, that is ER is cos theta, we extract it from what is given in the question. E theta is negative sin theta, E phi is cosine phi. Then we do the same thing like we did in the previous question. We substitute these components, ER, E phi, and E theta, and then we differentiate as required by equation number 19. So you can see the first term, the coefficient has been substituted and differentiation process done, and you get 2 over R times cosine of theta. The middle term the same, you substitute that coefficient, which was minus sine theta, and that sine theta was part of the equation. So you do that differentiation and you end up with the minus 2 over R times cosine of theta. Then you have also the third term, the same. So you're basically substituting the components that you have extracted from the vector field that is given, and then you differentiate. So when you do that, you come and say, you now substitute them back into this equation number 19. So when you do that, that is what you get, equation number 21. And then now you come to the Maxwell's equation. Okay, the Maxwell's equation connecting the charge density is given as divergence of E is equal to the charge density divided by the permittivity of free space. This is Maxwell's equation. So then you compare equation number 22 to equation number 21. They are both divergences of E, and then you now equate them so that you get what you can see there. The first two terms will cancel out and you remain with only the last term. So when you do that calculation, you get the charge density is E naught multiplied by negative sine phi over r sine theta. Then you can make a conclusion that equation 25 gives the expression for volume charge density. Its actual value can be obtained if we know the values of r, theta, and phi. Okay, so that's another application. Then let's look at an example number 3. A magnetic flux B is described in the cylindrical coordinate system. Cylindrical coordinate in terms of its two components. So we have been given the z component and the phi component. BR is unknown. That is, the first component is not known. If we assume that there is no phi variation in the magnetic field, find BR component of this field. It's a very interesting question. Now, we first try to find the component BR of the magnetic flux density using the fact that it should satisfy Gauss law. Gauss law is very important because it means there are no magnetic monopoles, and so it must be satisfied that the divergence of B must always be equal to 0. So we will let the derivative, phi derivative of the phi component be equal to 0, and if that is the case, we obtain the divergence. The equation that you see there is a divergence, and we have said that the partial derivative with respect to phi is equal to 0. So when you do that, the reason why you're even saying that it is equal to 0 is because the question says if we assume there is no phi variation, so the derivative with respect to phi is equal to 0. That is the term number 3 is equal to 0. So if you do that, then you equate the remaining parts, you get equation number 25. And so let me just see. Equation number 25 has a derivative with respect to z, so you need to carry out that differentiation, and whatever you get, you can see there. So actually, you can actually follow, because our interest is to find BR. Okay, so equation number 25 is just a matter of making BR the subject and carrying out differentiation where it is required. Okay, so that's basically what we have done here. And because now for you to get BR, you must integrate in the final stage with respect to R. Okay. If you did your calculus well, you should understand what I'm saying. You are making BR the subject, so you need to integrate at some point because you have a derivative with respect to R. So you do that and you get your R component of the magnetic field vector as what you can see there. Then we make a conclusion and say for the B field to be finite, the constant C must be 0. And therefore, if you put 0 there, you get your BR as a simple term, as you can see in equation number 26. So I want to believe that these are not complicated steps that will confuse you when you try to do them on your own. But I want to again encourage you to try and do these things on your own. You can follow the video, the explanation, and then try to carry out the integration, the differentiation, the application of the divergence and curl and all that, and then you prove some of the answers that are given. So that should be the end of our lecture. It is a short lecture that I just wanted you to get familiar with these new coordinate systems, the cylindrical and the spherical, because these coordinate systems will not only be applied in Maxwell's equation, but we will find them also in other uh, subsections of electrodynamics, like in the transmission lines and waveguides. We are going to deal with different forms of coordinate system. So it's important that you get familiar with these coordinate systems. So I don't want to say beyond that. Let me just wish you all the best and give me your feedback on how the video is. See you next time. Bye bye.